Hey guys, my name is IBM and I have decided to take you through waves and superposition. This is going to be waves and superposition, and I think these will be main lessons because waves and superposition, they're actually two in one. So there will be many lessons. It may take around 8 to 10 lessons. However, I'll try my level best to simplify the concepts under waves and superposition. Just remind you of the course outline. For AS Physics, you should study physical quantities and units, errors and uncertainties, treatment of uncertainties. When I say treatment, that is combination of uncertainties. You should be able to study kinematics, dynamics, force, density, and pressure, work energy and power, deformation of solids, waves and superposition, which we are going to explore, electricity and DC circuits, and finally particle physics. When you study these nine topical areas, you are supposed to be ready for AS Physics. Do not forget to watch the solved past paper questions for each of these topics, and do not forget to watch all those lessons. There is a playlist for each of these topics apart from those which are still in yellow. So let's go to waves and superposition. So in the Cambridge syllabus, waves is supposed to be unit 7 and superposition is supposed to be unit 8. But as for me, I don't always separate waves and superposition. I teach it as one topic. So as a teacher, I may also teach it as one topic, but they are actually two topics in one. So waves is unit 7 or chapter 7, and superposition is chapter 8. But I will teach it as 7 and 8 at the same time. So under waves, we shall see mechanical waves, which include transverse and longitudinal waves. So we shall be able to distinguish between transverse and longitudinal waves. It is the same concept you studied in IGCSE. We shall also talk about electromagnetic spectrum or electromagnetic waves, which are the same concepts that you mentioned in IGCSE. We shall talk about the two-source interference, that is now for AS level alone. We shall talk about diffraction and diffraction grating. You never saw that in in IGCSE. We shall talk about progressive waves. You might have mentioned them in IGCSE. We shall talk about stationary waves, where we shall be able to distinguish between progressive waves and stationary waves. We shall talk about Doppler effect, and I think you might have somehow mentioned Doppler effect in IGCSE, but not in much details. We shall also talk about waves on a c.r.o, where we shall do calculations to determine frequency, period, amplitude of waves on a cathode ray oscilloscope. So these are going to be the most important subject areas under waves and superposition. So let us just start straight away. This is going to be lesson 1. In lesson 1, we shall start with some of the concepts you mentioned in IGCSE in our introduction. So this is supposed to be unit 7.0, which is waves. I said this is 7.0 waves, and 8.0 is supposed to be superposition, but I'll just teach it as one topic. So I'll call 7.0 waves, and I may call 8.0 superposition, but still it will be under waves and superposition. Don't forget this is AS Physics, but these concepts are going to be useful for other curricula such as AQA, IB, and so on and so forth. So let us start with progressive waves. Let's start by talking about progressive waves. So what is a wave to start with? What is a wave? In IGCSE, you must have mentioned that a wave is any disturbance from an equilibrium condition that travels through a medium, transferring energy from one region to another without transferring matter. So your IGCSE teacher must have emphasized that a wave transfers energy but without transferring matter. The particles themselves do not move from one point to another point, but the particles pass on their energy from one point to another point. That is how a wave behaves. And in IGCSE, you categorize waves into both mechanical waves and electromagnetic waves. So you distinguished waves to be mechanical or electromagnetic. And then for mechanical waves, You mentioned that these are the waves that require a material medium for their propagation. Something mechanical involves work. And to do work, there must be a medium in which work is being done. So, mechanical waves require a material medium for their propagation. For example, sound waves cannot travel in empty space. They cannot travel in a vacuum. They require a medium of propagation, which could be air or a solid, and so on and so forth. Water waves will require a material medium for their propagation. In others, they would require water. Waves in a stretched string or a vibrating string. Waves in a helical spring, those are examples of mechanical waves. Of course, you can always refer to sound waves and water waves in this case for mechanical waves. These ones require a material medium for their propagation. So these waves are produced by a disturbance in a material medium and are transferred by particles of the medium moving or oscillating to and fro. So the particles are going to be moving or they will be oscillating when the medium is disturbed. So they will be moving or oscillating to and fro, thereby transferring energy from one point to another, or thereby transferring their disturbance from one point to another. So such waves, therefore, can be felt or they can be seen. We see water waves, we can feel sound waves because the medium is being disturbed and the disturbance is passed on from one point to another. So we can see such waves and we can maybe feel them. So such waves are said to be mechanical. However, these ones cannot travel into a vacuum. So mechanical waves cannot travel cannot travel through a vacuum because they require a material medium for their propagation. We are much aware that there is no material medium in a vacuum. It is just empty space without even air. So sound waves cannot travel through a vacuum because they require material medium. So these are mechanical waves. What is very important or a takeaway from here is that they require material medium. And the most important example is the sound waves or the water waves. And these ones cannot travel through a vacuum. So another takeaway from this slide is that a wave is a disturbance which involves transfer of energy from one point to another. Okay, on the other hand, we talked about electromagnetic waves. Of course, these are the waves that do not require any material medium for their propagation, and therefore they can travel through a vacuum. In your IGCSE, you mentioned all the 7 regions of the electromagnetic spectrum, which we shall still talk about in a special subunit called electromagnetic spectrum. And these include all the waves that you know that fall under electromagnetic waves, ranging from light waves or visible light, X-rays, radio waves, talk about UV light or ultraviolet rays, infrared rays, talk about gamma rays, and so on and so forth. So these waves consist of disturbances in form of electric and magnetic fields. So these ones we shall talk about them and a special category called the electromagnetic spectrum in more details. The most important thing to note about electromagnetic waves is their ability to travel through a vacuum. So the electromagnetic waves can freely propagate through a vacuum. They do not require any material medium for their propagation and therefore they can travel through a vacuum. We shall talk about the 7 regions of the electromagnetic spectrum. Here I gave 1, 2, 3, 4, 5, 6, but there are 7, ranging from radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. So we shall see these ones under a special category called the electromagnetic spectrum. Points note from what I've just talked. When we talk about wave motion, it involves transferring energy from one point to another without there being any transfer of matter between 2 points or between the points. The particles could just vibrate about the same point, passing on their energy to each other, thereby the energy propagating from one point to another. but without the particles themselves moving from one point to another. So energy is transferred without transferring matter. The particles in the medium do not move like I've said, instead they oscillate or they vibrate about the equilibrium position. For example, when we talk about electromagnetic waves from the sun, they carry the energy that plants need to survive and grow. So these carry energy that plants need to survive and grow, which is responsible, of course, for photosynthesis. The energy carried by sound waves cause our eardrums to vibrate so that we can detect the sound. If there was an earthquake, the energy carried by seismic waves can devastate vast areas, causing land to move and the buildings to collapse. So the energy is being transmitted from one point to another. Waves which move energy from place to place without transfer of matter are going to be called progressive waves. Later on, we shall distinguish progressive waves from from another type of waves which we are going to call stationary waves. Of course, the opposite of progressive is going to be stationary. So these waves, which we commonly talk about, that transfer energy from one point to another without transferring matter, are specifically called progressive waves. To progress, energy is going to be in motion. Energy is going to leave one point to another point, but there will be no transfer of matter. So progressive waves are those waves where energy is transferred from one point to another. Of course, for all waves, there is no transfer of matter. That is a progressive wave. We shall talk about progressive waves later on. How are waves generated and how do waves propagate? So, of course, for waves to be generated, there should be a source. And when they are generated, the particles must be the particles in the transmitting medium must be allowed to propagate. So, waves are generated when particles in a transmitting medium at any point are disturbed. So there should be a disturbance to cause or to generate a wave. And when there is a disturbance, then these particles start vibrating or they start oscillating, causing their adjacent neighbors to oscillate or to vibrate in return. So as the particles start vibrating, passing on their energy to the vibrating to the neighbors, cause them to also vibrate, then energy is going to be propagating from one point to another. So in this way, the vibrations continue from the source where the disturbance started from to other regions in the transmitting medium. That is, if there is a medium. So the disturbance spreads from the source outwards, and it continues, and it constitutes the waves. So a point must be disturbed, the particles start vibrating, they cause their neighbors to vibrate, and the disturbance continues to constitute what we call a wave. This is easy to see with the water waves, or it is also easy to see with a vibrating tuning fork. So for example, a vibrating tuning fork sets the air close to it into oscillation, and a sound wave spreads out from the fork. If you have seen a vibrating tuning fork hit on, say, a table, when you look at it, you see the fork vibrating, and even the air particles around vibrate. That's how we detect the sound coming from the tuning fork. Of course, for radio waves, the vibrating objects are the electrons. For radio waves, the vibrating objects are going to be the electrons. Of course, if we talk about radio waves, these ones are the ones responsible for radio communication, and the radio waves fall on an antenna of a radio. These are going to cause oscillation of charge carriers, or they are also produced by oscillation of charge carriers. So it is these oscillating charge carriers which produce the radio waves, and the same oscillating charge carriers or charged particles which pick the radio waves. So that is how waves are generated. There should be a vibrating there should be a transmitting medium if it is going to be a mechanical wave, and the particles at a certain point must undergo disturbance for the wave to be generated. Let's talk about the types of waves that you also mentioned in IGCSE. Types of waves. I think in IGCSE you mentioned that there are two types of waves. In IGCSE, you mentioned that there are two types of waves, I think. And the types of waves you mentioned in IGCSE were the longitudinal waves and the transverse waves. So although waves are mechanical and electromagnetic, although waves are progressive and stationary, as we shall see later on, waves exist in two types. We have what we call longitudinal waves and transverse waves. Longitudinal waves are mostly mechanical, but transverse waves can be both mechanical and electromagnetic. Longitudinal waves are mostly mechanical, but transverse waves can be both mechanical and electromagnetic, as we shall see. So what is the difference between longitudinal waves and transverse waves? In IGCSE, you distinguished transverse waves from electromagnetic waves, and you used the different diagrams to show the difference. So the difference between transverse waves and longitudinal waves will be demonstrated using these two animations. The animation on top is for a longitudinal wave, and the animation at the bottom is for the transverse waves. So remember, for both waves, the particles themselves are not expected to move from one point to another. They're supposed to oscillate about the same point. So in this animation, I use the red to represent the particles to be able to distinguish a longitudinal wave and a transverse wave. For longitudinal, the black vertical line is the equilibrium position, or the point where the red line would be if there was no oscillation. However, what is really happening is that the red line moves some distance to the right-hand side and some distance to the left-hand side. However, you look at the compressions propagating towards the right-hand side. So the wave is moving towards the right-hand side, and the red line is vibrating towards the right and the left, or the red line is oscillating towards the right and the left as the compressions move towards the right-hand side. So this is going to be the direction of the wave, and this is going to be the vibration of the particles. So what do we notice about the longitudinal wave? The particles vibrate parallel to the direction of propagation of energy. The particles in the longitudinal wave vibrate parallel to the direction of propagation of the wave energy, because the energy is moving towards the right-hand side, but the particle is vibrating to the right and the left. So it's like the particle is vibrating parallel to the direction of propagation of energy. Let's look at the transverse wave here. We are seeing that the energy is propagating from left to right. So this is the direction of energy, or the direction of the wave. But I said I represented the red with red to be the position of the vibrating particle, and we have noticed that is vibrating upwards and then it vibrates downwards. So you notice that the direction of propagation of the energy is like this, from left to right, yet the particle is vibrating up and down, meaning that the direction of vibration is making an angle of 90 degrees to the direction of propagation of the wave, or to the direction of propagation of energy. So what is therefore the difference? For a longitudinal wave, the particle vibrates the particle vibrates, or the particles vibrate parallel to the direction of propagation of energy. And for a stationary wave, for transverse wave, the particles vibrate perpendicular to the direction of propagation of energy. In both cases, I'm mentioning particle or particles. It is the particles which are vibrating in this case. It is the particles which are vibrating in this case. For longitudinal, they vibrate parallel to the direction of propagation of energy. For transverse, they vibrate perpendicular to the direction of propagation of energy. That is the major difference between these two. So we are saying for a transverse wave, a transverse wave is one in which the vibrations of the particles in the wave are perpendicular. That means at right angles to the direction in which the energy of the wave is traveling. The vibration of the particles is perpendicular to the direction of propagation of energy. That is a transverse wave. For transverse, the vibration of the particles is perpendicular to the direction of propagation of energy. That's what we mean by transverse wave. The particles vibrate at right angles to the direction in which the energy of the wave propagates. That is transverse. Some of the terms we may talk about under transverse could be explored in our next slide here. So we have said for a transverse wave, the particles vibrate perpendicular to the direction of propagation of energy. For instance, in this example of a rope, the hand moves the rope up and down, and as the rope vibrates, the wave propagates through the rope in this direction. So the wave is propagating from left to right. So if a wave travels down a rope from the left to the right, as shown above, the particles of the rope vibrate up and down in a direction transverse. When we talk about transverse, we mean perpendicular or at right angles to the motion of the wave itself. So the wave is propagating from left to right, and the particles of the rope must be vibrating up and down. There is, of course, no transfer of matter. In the previous slide, we have seen that the red spot was not moving from left to right. In this animation here, you notice that the red spot concentrates along this line here, but the wave is propagating from left to right. So there is no transfer of matter from point A to point B in that rope. However, energy is being transferred. So that is a transverse wave. No matter is being transferred, but energy is being transferred from one point to another point. In a transverse, the particles vibrate perpendicular to the direction of propagation of energy. Examples of transverse waves, you mentioned these ones in IGCSE. These include light waves. When I talk about light waves, I mean electromagnetic waves. These are 7 regions ranging from Reed's mother is visiting Uncle Xavier's garden. That is from radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. Reed's mother is visiting Uncle Xavier's garden. All these ones are going to be transverse waves because they travel as vibrations of electric and magnetic fields which are always perpendicular to the direction of propagation of energy, as we shall see later on in a unit called, or in a subunit called, electromagnetic spectrum. So light waves are electromagnetic waves. Talk about the surface water waves. Waves on the surface of water are transverse because the particles vibrate up and down as the wave spreads on the surface of water. We also have waves during earthquakes, and these are called the seismic waves, particularly the secondary seismic waves. Of course, during an earthquake, there are 2 types of waves. We have the primary waves, which we call the P waves, and we have the secondary waves, which we call the S waves, or the secondary seismic waves, which we call the S waves. So during an earthquake, these 2 types of waves are propagated through the ground. There are those which are transverse. In other words, they cause the ground to vibrate perpendicular to the direction in which the earthquake is propagating. And there are those which cause the earth to vibrate parallel to the direction in which the earthquake is propagating. So those waves which are propagate perpendicular to the direction in which the earthquake energy is propagating, we call them the secondary seismic waves, or simply the S waves. We also have waves on a string or in a rope like this one here. These are actually transverse waves. Of course, the common transverse waves you always mention are light, water waves, and then the S waves. Those are the common examples we'll always mention. Now, one important thing you need to note is that transverse waves normally have crests and troughs. They normally have crests and troughs. So we shall define this as a crest. This has a crest, this is as a crest, and this has a trough, and so on and so forth. Of course, the highest point or the highest point of disturbance from equilibrium position is what you call the crest in IGCSE. And the lowest point of disturbance is from the equilibrium position is what you call the trough from IGCSE. So transverse waves always have crests and troughs. Those are peaks and valleys maybe, or hills and valleys if you want to call them. And the distance between one peak and the next peak, or the distance between successive crests or successive troughs, is what we shall call the wavelength. You mentioned that the distance between one peak and the next peak, that's why I'm using the word successive. Another word to mean successive would be adjacent. The distance between two adjacent crests. Adjacent means one to the next without skipping any. Successive also means one to the next. So from one peak to the next, the distance between one peak to the next, or one trough to the next, is what we are going to call the wavelength. So those are the transverse waves. Let's also draw more information about the longitudinal waves. How shall we define longitudinal waves in an exam? So we said for longitudinal waves, particles vibrate parallel to the direction of propagation of energy. And this is a good animation for us to represent this. So the red line is showing the direction of propagation of energy. And we notice that the red line is moving from left to right. The black dots are representing the particles themselves. And we are seeing that the particles are just vibrating to and fro. They're just vibrating to and fro. So the particles themselves are not moving, but the energy is being propagated through these particles from left to right. So this time the red line is showing the energy, the direction of propagation of energy. And the particles are represented by the dark dots. So you also notice that where the particles are very close to each other, they are under high pressure. It is equivalent to a crest. It would be equivalent to a crest, but we would call this one we shall not call it actually a crest. We shall instead call it a compression if we are talking about longitudinal wave. So a longitudinal wave is one in which the vibrations of the particles in the wave are parallel. So we say the particles vibrate parallel or along the direction in which the energy of the wave is traveling, or the direction in which the energy of the wave is propagating. So for a longitudinal wave, the particles vibrate parallel to the direction of propagation of wave energy. The particles vibrate parallel to the direction of propagation of wave energy. So as the wave energy in this case is from left to right, we are seeing that the red dots are moving backwards and forwards. They are moving to the left and to the right. So that's why we are saying the particles vibrate parallel to the direction of propagation of energy. Of course, the examples you mentioned in IGCSE include the sound waves. We have the P waves. So the sound waves and the P waves are going to be the most common examples of longitudinal waves that we'll always mention. Waves in acoustic pipes, those are sound waves. Or the primary seismic waves, which I talked about, and during an earthquake, where these ones, during an earthquake, these are waves where the particles, or which cause the ground to vibrate parallel to the direction of propagation of the earthquake, or the direction in which the earthquake energy is propagating. Of course, we can also produce waves in a helical spring, but because a helical spring can produce both longitudinal and transverse waves, depending on how you move it, we shall just talk about sound waves and the P waves, or the primary seismic waves. So Those are longitudinal waves. Some of the terms which may be mentioned or which we shall talk about under longitudinal waves include the compression and the rarefactions. So I say the crests. What would be like a crest on a transverse wave is going to be a compression on a longitudinal wave, and what would be like a trough on a transverse wave is going to be a rarefaction on a longitudinal wave. You notice that what is represented as a crest is correspond to high pressure where particles are very close, they are compressed together. And you notice that where there is a valley, the particles are further apart, they are under low pressure. So we shall call that one a rarefaction. So when you talk about longitudinal waves, you should be thinking about compressions and rarefactions. So like I said, a helical spring can easily produce both transverse and longitudinal waves. So in this in this picture here, I represented a longitudinal wave on a helical spring, where we notice that at some point the coils are very close to each other, and at some point the coils are far from each other. So the energy, the vibrations of the coil are going to be to the left and to the right, but we expect that the energy is moving towards the left towards the right hand side. So longitudinal waves are readily formed on a stretched slinker spring by alternatively compressing and expanding one end as shown above. In every laboratory there should be a slinker spring. I want you to note that the spring coils vibrate along the length and do not move from A to B, but a series of compressions and expansions, which we shall call rarefactions, propagate along the spring. So in the laboratory, you can tie a red ribbon or a ribbon onto the coils and see. Of course, you will see energy propagating from the left to the right, but you'll see the ribbon just vibrating or oscillating about the same point. So the compressions and rarefactions propagate from A to B, but the coils themselves do not move from A to B. So we have now compressions and rarefactions. So a compression is going to correspond to a region where there is high particle density. The coils are very close to each other. High particle density. The particles are compressed. That's why we're calling it a compression. A point or a region where there is high particle density, or regions where there is high particle density, where particles are very close to each other. That is going to be called a compression. On the other hand, a rarefaction is going to represent, or rarefactions are regions of low particle density. This is only in a longitudinal wave. We don't expect compressions and rarefactions in a transverse wave. So rarefactions are regions of low particle density. Compressions are regions of high particle density. One important thing I want people to note is that I have labeled the distance between this compression and this compression to be wavelength. Or I could also have named the distance between this rarefaction, the center of course, and the center of this rarefaction. I would also label this wavelength. So the distance between successive, I always want to use the word adjacent. Distance between adjacent compressions or adjacent rarefactions is going to be called the wavelength. I say that the word adjacent or successive means one to the next without skipping any. So distance between adjacent compressions or distance between adjacent rarefactions is called the wavelength. And I think you mentioned the same thing in IGCSE. So in comparison of the two, we note that for a longitudinal wave, the particles vibrate back and forth. The compressions propagate into the medium from one end to another end. That is for a longitudinal wave. The particles move back and forth. So this, the red spot is showing, or the red arrow is showing the movement of the particle. and note that the particle is moving to the left and to the right. But we see that the energy, which is represented by the black spot or the black arrow, the energy is moving through the particles from left-hand side to the right-hand side because the rarefactions and the compressions are propagating from the left to the right-hand side. So that is a longitudinal wave. Yet for transverse wave, we notice that for transverse wave, the particles vibrate up and down in this case. But the wave energy is propagating from left to right, which makes an angle of 90 degrees. So for transverse, the particles vibrate perpendicular to the direction of propagation of energy. The crests and the troughs move from left to right or propagate from left to right because the energy is passing through them, or it is forcing them to propagate from left to right. But the particles themselves do not move from left to right. They vibrate about the same position. Yet, for longitudinal, the particles move back and forth. They vibrate parallel to the direction of propagation of the wave energy. So you should mark the difference between those two. Here I gave an animation using a loudspeaker as one example of a source of longitudinal waves. Of course, the loudspeaker has a cone which makes the air around the loudspeaker to vibrate, causing the air particles to move back and forth because the cone of the loudspeaker moves in and out of the loudspeaker. So because it is moving in and out of the loudspeaker, it is causing the air molecules around the loudspeaker to compress and stretch out as the compressions and rarefactions propagate through the air up to your ear so that you can listen to the sound. So that is the summary or the summarized comparison between a longitudinal and transverse waves. So in summary, when we talk about a transverse wave, the particles vibrate perpendicular to the direction of propagation of wave energy. For longitudinal, the particles vibrate parallel to the direction of propagation of wave energy. You must refer to the particle. The particles of longitudinal vibrate parallel to the direction of propagation of wave energy. The particles of transverse vibrate perpendicular to the direction of propagation of wave energy. Of course, later on we shall see that transverse waves undergo polarization, and this is what distinguishes them from longitudinal waves. Because their particles vibrate in more than one plane, it is easier to polarize waves. We shall see what we mean by polarization as a subunit in this topic. Longitudinal waves do not undergo polarization after all. The particles vibrate in the same direction or parallel to the direction of propagation of wave energy. We have given examples of transverse waves to include light waves. And here we wrote, we gave also S waves. And here we gave P waves. So you should be able to distinguish between transverse and longitudinal. And you should be able to know that transverse waves undergo polarization and longitudinal waves do not undergo polarization. You should be able to give light waves or electromagnetic waves as an example of transverse waves. You can also give S waves as an example of transverse waves. You should be able to quote sound waves as an example of longitudinal waves and P waves as an example of longitudinal waves. I think lesson 1 should end there. See you in lesson 2. Until next time, bye bye.